Hello, everyone. It's me, Brooke, from a different setting today. I'm in the dorm room. So today we're going to talk about transformation geometry. Let's see, what is transformation geometry? Transformational geometry is the use of geometric transformations such as translations, reflections, dilations, and rotations to prove geometric properties. It is quite different from the traditional use of proving theorems in Euclidean geometry. These concepts are taught to elementary and middle grade children by using simpler terms such as flips, slides, and turns. Flips represent reflections, slides correlate with translations, and turns display rotations. Reflections occur across the x-axis, y-axis, or a straight line. Rotations can be formed by turning an object by 90 degrees. Translations move an entire figure up, down, left, or right based on the given units. For example, a trapezoid can be translated 5 units down and 2 units to the left, and dilations change the shape of an object. So more about transformation geometry. It contains a wide variety of applications from elementary mathematics to upper level concepts like physics. Transformations can be done on quadratic and cubic functions as well as linear ones. Algebraic equation transformations. The algebraic equation for transformations is f of x equals a times b of x minus h, all to the power of n plus k. For this equation, a is the vertical stretch, b is the horizontal stretch, h is the horizontal shift, and k is the vertical shift. Transformations can be done on any x and y axis, whether positive or negative. Upward shifts are displayed by f of x plus n, and downward shifts by f of x minus n with x in parentheses by itself. Shifts to the left are shown by f of x plus n with x plus n in parentheses, and shifts to the right are written as f x minus n with x minus n in parentheses. One object can be have multiple types of transformations. For example, a square can be rotated and reflected. So you can do more than one of these types of transformations on a single object and see how it changes across the positive and negative x and y axes. So somebody who is very prominent with the study of transformation geometry is Felix Klein. He lived from April 25th, 1849 to June 22nd, 1925. His full name was Christian Felix Klein. He was a mathematician born in Germany who is credited with being the first person to use transformations in geometry. In 1872, Klein published his work called Erlanger Program, which discussed his findings on geometric variations and transformations. In 1912, he received the Copley Medal from the Royal Society of London in London, England. The medal rewarded Klein for all of his mathematical research. This award first made an appearance in 1731 and is given to an outstanding math or science researcher each year. He worked with several different mathematicians and professors throughout his lifetime. He went on to become a professor himself after graduating with a PhD in 1868 from the University of Bonn in Bonn, North Rhine-Westphalia, Germany. Next, we have Julius Plucker. He was born on June 16, 1801, and died on May 22, 1868. Plucker was also a German mathematician. He made contributions to physics, projective geometry, and analytic geometry. In 1829, he began teaching at the University of Bonn and mentored Felix Klein through his doctoral studies. The two conducted many tests and experiments through math and science together. He attended 4 different universities in Europe. In 1866, 2 years before his death, he received the Copley Medal for his studies in magnetism, analytic geometry, and spectral analysis. He published his writings on analytic geometry in 1831 and proposed the idea that lines are more prominent in geometric configurations than points. He used this theory when conducting research for projective geometry, and which led him to create a dual principle concerning theorems that if one theorem is accurate, then when switching components within the theorem, it would still be accurate. So some more information about Klein and Plucker. After Plucker's death in 1868, Klein worked on his last book to complete the writings and published it. Both men worked with several different researchers throughout their careers from countries including Germany, Berlin, and France. Plucker began studying magnetisms and crystals after realizing his geometry research opposed another European studies. He spent the last 20 years of his life working with Robert Bunsen, a German chemist who created the Bunsen burner we know today. I got really excited when I was looking online at research on Britannica about Plucker's friends and who he was working with. And when I saw Robert Bunsen, I was like, oh, that has to be the chemistry Bunsen burner. So I thought that was really interesting and neat to include in here. and he also worked with Johann W. Hittorf, which was also a German physicist. So, since there was some controversy at the time with Plucker's research in some mathematical areas of geometry with someone else's, he decided to start studying another field, which made sense, but also I would have enjoyed seeing more of his work in the geometry field. I wonder what else he could have, discovered. And so Klein did many discoveries with Sophus Lee, who was a mathematician from Norway, in transformation geometry and differential equations. So now we're getting into some more algebraic type things and with some calculus. Both men have their writings published in journals and books. They are both still highly respected among the math and science community. So both of these men were prominent in transformation geometry discoveries. They are both highly credited with the geometry itself, and both have journals and entries with all of their work published in different areas of the world today. So someone else that I found online is Andrei Kolmogorov. He lived from April 25th, 1903 to October 20th, 1987. He was a Russian mathematician, so not from Europe this time, but from Asia, and who made discoveries in a variety of mathematical fields such as algorithmic theory, probability theory, information theory, the physics concepts of fluid and stochastic properties, statistics, and nonlinear properties. He was a professor at Moscow State University after graduating from there in 1925. He did not uh, he did not become a professor automatically right after graduating with his bachelor's degree. He went and got his PhD and then came back as a professor. In 1965, he received the Lenin Prize. He was also recognized 7 other times by the Order of Lenin. This reward was given by the Soviet Union to researchers in a variety of fields, not just math and science. So there were also other people that would receive this award, whether in poetry or art, business, economics, history, different areas, but he received many rewards for his math and science discoveries. A fun fact about him, he studied Russian Alexander Pushkin's poems and developed quantitative analysis on them. So as someone who has not taken quantitative analysis and someone who is not going to, I've heard a lot about it from some of my friends, and they're all very stressed about when they take quant for the ones that have and the ones who are currently in it. So for him to do this on a poem is very interesting and very impressive. I wonder what that looks like. And then here are my references. So the next thing I'm going to talk about are a couple of proofs that I have here. So the first proof that I have is about rotations, and it says that I'm going to read it to you. Let's see. I think I can make this work. So EF and GH are parallel lines, and the measure of angle EFG is 40 degrees, and we're supposed to find the measure of angle X. So here's what our image looks like. See if we can straighten this up. Here we go. Here's our image. We have that EF and GH are parallel lines right here, and we have the measure of angle EFG is 40 degrees, which we have placed right here. And now it says the proof, we are given EF and GH are parallel lines, and the measure of EFG of this angle is 40 degrees. Let's see, the following will happen. So ray FE maps onto ray GH maps onto ray FE, and line FG maps onto itself. So I'm trying to read this from behind it. And therefore, the image of angle X will be exactly where the pre-image of angle EFG was. So the measure of angle X equals the measure of angle EFG. By the definition of rotations, measure of angle X equals 40 degrees. So since we're going to be doing a rotation here, when we rotate our lines around, so we have the FE, which is this line right here. When we rotate it around, it's going to match up with GH, and then GH would match up with FE. It would go back around the other side, and then FG would just match itself. So there's not a line that's going to correlate with that one. And so as we can see that when we move E over here, it's going to line up with this angle. These two angles will line up and they will equal each other. So that's on rotations. And then the second proof is about translations. So here we have another image. We have another set of parallel lines, except this time the parallel lines are vertical instead of more horizontal. And then we have one line going perpendicular and through them. Actually, it's not perpendicular, but it's going one that cuts through them. So we have that we are given the lines AB and CD are parallel, and the measure of angle DAB equals 60 degrees. And this time we're finding the measure of angle S, which is right here. It says if we perform a translation along the directed line segment, sorry, I had a small issue with one of the lines that I wrote down. So the directed line segment DA, which is this one right here, we can get a little bit closer. So DA, if you see that line segment, we will see that line CD maps onto line AB and line DA maps onto itself. Therefore, the image of angle S will be exactly where the pre-image of angle DAB was. So the measure of angle S will equal the measure of angle DAB. By the definition of translations, the measure of angle S equals 60 degrees. So if we see here, we have DA is going to map onto itself. And then we have angle S right here. Angle S right here is going to equal DAB when you do the translation. So this is my geometry, transformation geometry. I hope you learned something today, and thank you all so much for watching.